at this session. Please, I'm going to play a short video that is going to inform our session today so that then we can be able to have a quick interactive session before we get into the big details of what I've prepared for you. So enjoy this video.
In this video, I'll cover the fundamentals of vertical curves and vertical alignment. Vertical curves are used to provide a smooth transition from one grade to another, similar to horizontal curves. Except in this case, we're looking at the vertical perspective. So we're looking at a profile view of our roadway. So imagine us kind of at the side of the road, and so we can see the grade coming uphill, the grade going downhill. In this case, that's the scenario we have. We have the entrance grade, which is known as G1, which then transitions to the vertical curve, which transitions back into the grade, the exit grade, which is G2. So we'll use that terminology, G1 and G2. When we're looking at vertical curves and vertical alignment, on the x-axis, we're going to see the stationing, and this is always in horizontal distances. So we're using the distances measured horizontally to represent the distances in the vertical plane. So everything is just a horizontal distance. And that really simplifies things for vertical curves. The vertical curves I will cover will assume will all be symmetric parabolic curves. So symmetric means that they're equal on each side of the PVI. So there's symmetry within the vertical curve. And parabolic, meaning that the parabolic equation defines the shape of the vertical curve. On the y-axis, we'll see the elevation as we move along the grades and the vertical curves. There are two primary types of vertical curves: a crest curve, where we have that concave down shape, and then a sag curve, where we have the concave up shape. The PVI is a very important point for vertical curves. These are where the two tangents meet, or the two grades meet. So we have a G1, it's our entrance grade. We have G2, which is our exit grade, and those two grades will intersect at the PVI, the point of vertical intersection. We also have the PVC. This is the point where the curve begins. This is the point of vertical curvature. So leaving entrance grade, G1, and starting to curve along the vertical curve. Then we'll reach the PVT. The PVT is the point of vertical tangency. This is the point where the curve ends, and we return to the exit grade, or G2. We use the term x to denote any horizontal distance along the curve. So x can be as small as 0, which would align with the point of the PVC, or as long as L, which is the full length of the curve, which would correspond to the PVT. And usually we're looking for the elevation of the curve at the point X. So X is typically some point of interest in the analysis. We use the capital letter Y for the elevation of the point along the curve that corresponds typically to our distance X. So we have X is our horizontal distance, and Y is the elevation of the point on the curve that we're interested in. Breaking that down a little bit more, so looking at
Thank you very much. We are done with the first bit, which is just understanding the geometry. So I would like us just first, please, we may mute so that at least we can be able to listen to each other. Thank you very much. Thank you very much. Now, the first thing that I want us to do is to be able to understand our levels of knowledge for this very topic. So what I would want you to do is introduce yourself and possibly say your level of experience when it comes to the design of vertical alignment of roads, so that then we can be able to build a very good background so that also we all feel that the session will be of use to all of us. So please, you may unmute, introduce yourself, tell us your level of experience in the design and what are your expectations. So please, you may take it away.
Good, e- good evening.
Good evening, sir.
Hello, I'm Osinachi from Nigeria. From the vertical alignment, I have a little experience about it. But where the problem used to be is at the sag area, because when that is at the crest, I used to have a very fine curve, but making a decision at the crest is always where the issue lies. So that's where I would want to get more information on, because the crest is always challenging to make a thorough decision, because you may have crest at the other hand, crest at the other side, then sag. Therefore, you might be thinking of how to make a very smooth curve at the crest, at the sagging side of it. So it becomes an issue. I have a little knowledge about it, so that's why I'm here to put myself right on making the right decisions. Thank you.
Okay, thank you very much. I think that's well in order. Thank you. One more person.
Hello.
Yes,
Good
please.
evening.
Good evening.
Yes. My name is Serge. I'm from South Africa. I'm a civil engineer, and my field is transportation, which is road design. But I've been doing design, but mostly water. I just did one design on the road, but I can say I don't have enough experience on horizontal alignment, but I got all the background from the schools.
Okay, thank you. Thank you. One more person.
Good morning, ladies and gentlemen.
Good afternoon. Good evening.
Good evening. My name is Radiani from Nairobi, Kenya. I do work in a design office. I'm looking forward to getting more insights on vertical design. My biggest challenge tends to be, especially in urban settings, where we have restrictions on our right of way and the interplay between the vertical and the horizontal alignment. Sometimes you find that our design manuals and whatever design criteria we are following tends to make it difficult to remain within our restricted right of way. So I'm looking forward to at least getting some more insights on how to solve this particular issue. Most of the time you find most of the errors in our vertical and horizontal designs tends to be the interplay between the vertical and the horizontal. So I'm looking forward to getting more knowledge on that. Thank you for this platform.
Thank you. Thank you, Martin. Thank you, Martin. One more person.
Good evening.
Good evening, Juma.
My name is Mutambo Juma from Zambia. I'm a water engineer. I have got interest with the road design. So I just saw this and I said it's my opportunity for me just to see what goes on the road design. Thank you.
Thank you very much. What I'm hearing is it's your first time possibly being able to start on a design. So thank you very much. And I hope that this session is going to be of help to you and many others. So thank you. Please allow me to start to paint a picture. But just before that, I can see we have some lady engineers here. So please, if you're a lead engineer in the building, you may represent your fellow ladies as we get into the thick of things now.
Yeah,
Please.
hello, evening.
Good evening.
My name is Priska. I am from Tanzania. I'm a pavement materials engineer by profession. So I'm more versed into pavement and pavement materials design. But in this alignment design, I'm fairly new. So I'm very eager to see what this entails. Thank you.
All right. Thank you very much. I think that is well put. So without much ado, I would like you to give me permission to start at once with what I had prepared for you. I will try as much as possible to cover the fundamentals. I don't know why I'm getting some echo from my side. I think some people are muted or unmuted. So please let us mute so that then we can be able to have a very crisp recording after this session for future reference. Thank you. In case you have any question, I would request that you may share it in the chat box, and I will take a moment to respond to all of them. Additionally, as we proceed with the presentation, please feel free to have whatever question you may have concerning a specific topic or whatever information that you may feel is adding value to the conversation. Please feel free to share it in the chat box. As we proceed with this presentation, I will be having some breaks after every 20 minutes so that then we can be able to interact and internalize with the concepts all together. This session is meant to build in information both for the beginners and also people who have a little bit of an expertise in this area. I will be using AASHTO American Standards as one of the reference materials. And at the same time, I'm going to be looking at the Kenya Road Design Manual, the 2025 version, which has greatly tried to incorporate both the Indian Road Congress, the American standards, and of course, with contextualization with our specific needs here. Please remember that what we'll be setting here is foundational principle and therefore can be used in any other country. And of course, you can be able to use these very techniques to apply your local road design manuals. So the first thing I want us to start with, let me just remove this. The first thing I want us to start with is this diagrammatic picture that we have here. So I want you to do this. I want you to picture yourself. I want you to picture yourself in these two categories. Number one, you're currently the road design engineer. So you're the person who is designing. Well, the second one is the person who is driving. And I want you to picture yourself as the person who is driving in these red Lamborghini or whatever it is. And I want you to picture yourself driving along crest curve and a sag curve. So a sag curve, a crest curve is when you're going uphill. And as you're going uphill, I want you to imagine these cows crossing at that specific point. Please paint that picture, because that picture is going to help us a lot as we proceed to the very last point of this. We'll keep referring to that picture so that then we can be able to visualize the impact of our decisions to the road safety and various users of the road at that point. Fantastic. Now, number two, when we talk about vertical alignment design, I want you to picture this as if you are seated on the side of the road. So you are looking at it from the side. You're seated at the beach. What do you see? what do you see? You just see a line. You see just the outer rim of the road. That is what we call the vertical alignment. So you'll be seeing the road going up and down. Please, for those who want to record the rest session already is being recorded, and the recording will be sent to your emails immediately it's ready. So please don't worry. So back to the picture. So you're sitting, imagine a road construction is happening, and you're just sitting on the side of the road at the ditch. Your view, which is the side view at that point, is what we call the vertical alignment. You'll see the road going up and down. Now, let's go to the design. How do we approach it? So the major control for the design of vertical curve is what we call minimum sight distances required. Now, the major sight distance that we consider when it comes to the design of vertical curves is the stopping sight distance. For crest curve, the absolute minimum of size of that curve is decided by the stopping sight distance. Then the desirable is decided by the passing sight distance. Take note of that. The minimum values for vertical curve that is the absolute minimum, is decided by the stopping sight distance, while the desirable is decided by the passing sight distance. What is the minimum stopping sight distance, or what is stopping sight distance? A stopping sight distance is the distance that is required by a driver to safely bring the vehicle to a stop in case they see an obstacle along the road. So then, as the design engineer, your work is to ensure, should any obstacle appear anywhere along the curves, then the drivers can safely be able to stop. That is the key and the most important part. Now, the other factors that play in role or rather we consider as design engineers, which is of course drainage requirements. So as you do your design, the vertical alignment, your choices and your decisions are going to majorly influence the drainage of the road. So we have seen scenarios where we have water stagnating on the ditches. And we have also seen scenarios where water is overtopping the road. We have seen scenarios where the culverts are not well placed, and then that becomes a drainage issue. The other thing is the comfort of the road users. But most importantly, as we consider these factors, the vertical curve should be simple in application and should result in a design that is safe, comfortable in operation, and pleasing in appearance, and at the same time adequate for drainage. So then the objective for the design of vertical curves is, number one, a design that is safe. That is why stopping sight distance and passing sight distance is the most important aspect. It's the major controlling factor. The second one is comfort. How you design your vertical alignment will greatly affect the comfort of the road users. Lastly, pleasing in appearance. Of course, we're going to be seeing that because we're going to be designing a road section right today. Osinachi, please, you may mute. Please let us mute so that then at least we don't get distracted. Brian Bosire, you may mute, please, if you find it a good thing. Thank you. As you do the design of your vertical alignment, you will be influencing the following. Now, at this time, we are not looking at the design phase, we are looking at the outcome. We are looking at the final output that you decide as the design engineer. What will be the implication to the road users? Number one is what we call vehicle speed. So this is controlled by the gradient. This is controlled by the gradient that you choose. What speeds will the vehicles be able to operate under? So for example, if you decide to have very steep gradient, then vehicles will be driving below even the design speed. If you are in a rolling terrain, again, the slope that you have influences the speed of your vehicles. Number two is drainage. This is of importance. Again, the slope that you choose for your various sections. Then there is the economy of transport. I think this is one that most people don't pay attention to. The economy of transport is, again, I was talking to some engineers from Tanzania, and they were saying there is the road that crosses around the coast section of Kenya and going all the way to Tanzania. And you notice that the long distance transporters tend to avoid it because the curves are a little bit too steep, you know, and therefore they find it high consumption of fuel, of course, because the section is a bit hilly, and therefore the slope is brings the design engineers and quite a steep slope. And then there is the aspect of road safety. Again, stopping sight distances, passing sight distances, and headlight glare. And then construction cost. There are two perspectives that are very important for you to have in mind. When it comes to on roads carrying large traffic volumes, balance should be reached between road user benefit and the construction cost. So this explains the reason as to why you will notice in expressways, the slope of the road or the gradient of the road is sometimes recommended to be even below 4%. That then explains why you will always notice very heavy earthwork along major roads. Along roads that have very high traffic volume and capacity, you will notice the government invests a lot in major earthworks to make sure that the slope is below 4%. So then the economy of transport, at that point, the cost of transportation is lower. The carbon emissions, again, we get to be able to take care of that all together to minimize the emissions on the road. Whereas when you go to lightly traffic roads, which is, for example, rural roads, the road user savings are less significant. It does not mean they are not important. And the alignment that gives the lowest cost of construction within the limits of the chosen design criteria should be adopted. So then, that's why you notice in low traffic roads, you will not find a lot of earthwork ongoing. You will find steep slopes at that point. Again, the economy of transport, comparing that people that are moving within that road, then again, we have a saving. Now that we've been able to create a foundational knowledge on that, do we have any question up to that point before now we get to the design elements? Do we have any question at that point? Very well. So now at least we have understood greatly the impact and influence of our decisions as the design engineers. Drainage, road safety, comfort, cost of construction, those are the primary aspects that our decisions are going to influence. Now, let's look at the various design elements that we use to achieve those objectives. Now, the profile of a road consists of a combination of a straight section, those are the design elements, a straight grade, and a vertical curve. And in the vertical curve, we have a crest and a sag curve. The profile provides smooth transition between two consecutive gradients. So what this means is we are able to move from one elevation to another, one elevation to another. The design elements are straight grade and vertical curves. And these vertical curves they are defined by the parabola equation, because the parabola provides a constant rate of change of curvature, and hence we can be able to maintain proper acceleration and visibility. We'll be talking about how this parabola equation, and we have some factors called K values, that helps us to maintain that rate of change of curvature along the road section. So what you can see in the diagram here is basically the geometry of vertical curve, and that is why we are talking about, that's why it's called geometric road design. So at the very first point, at the axis, these are the elevations. So we are having elevations moving up from, let's say, 50, 60, 70, 80. These should be in meters. And of course, the reference point is the datum can be the sea level or some other datum that is chosen. And then along the x-axis, we normally have what we call the stations or chainages. So these will be 0, 0, 0 plus 100, all the way to the last stations at this point. Now, in this very geometry, we have the first element of design. Let me change the color of my pen. The first element of design, that is entrance grade, and this is what we are calling a straight grade, and the units here is represented in percentages. So we can have a slope of 10%, 15%, 2%, 3%, and all of that. So when we have an entrance gradient into the curve, we also have an exit gradient out of the curve. It is represented by G2, and this one is G1. Remember, when we do calculations of various factors in a vertical curve, we are going to be considering the G1 and G2. You will also notice that these slopes are moving in opposite direction for us to form proper geometry of this curve. Over and above that, we have a point that is called a point of vertical tangency. We can see here, it's PVC. This is the point where, in a layman's language, where we leave the straight grade and start getting into the curve. Again, there is a PVT, which is a point where a vehicle exits the curve and now gets, that is the vertical curve, and gets again back to the straight gradient. This again is the basic geometry. You must have this geometry in mind before you go into any design work. Because, for example, there is this point also called a point of vertical intersection. It's PVI, which is a point of where the two tangents intersect. So basically, if you draw a tangent along the straight section from the entrance grade, and the straight section from the exit grade, where they intersect, we have a PVI. This PVI is very important, especially when it comes to setting out of these vertical alignment, and of course, what we call facing of the alignment, whereby you coordinate the vertical alignment with the horizontal alignment as you harmonize your design. So this is basically the geometry. You can take a screenshot, you can take a picture of it. This is very critical. This is very critical because you cannot do any design without necessarily having an understanding of this factor. Now, let us now look at the two types of curve. These are the only two scenarios. I tell people that road design is the easiest, yet the most delicate kind of design that you will do. It's quite easy and straightforward when it comes to the look of things. But then when it comes to the actual application, then it becomes a little bit of a challenge altogether. So the types of vertical curves are applied again to effect the transition between this gradient. And the two types is the crest and the sag curve. So you can see the first one is what we call a crest curve. So we are moving uphill. And there is one important factor I want you to take note of it. This is letter L, which is the length of the vertical curve. This is the length of the vertical curve. It's very, very important. We always aim to achieve a symmetrical curve. So a symmetrical curve is something that we can be able to have two equal halves. That's why you're seeing L over 2 at this point. You will notice the PVI is the same, the exit grade and entrance. Please note that the length of the curve starts from PVC, which is point of vertical curvature, all the way to the point of vertical tangency. We're going to be seeing how this is replicated in real life, for example, as we design our civil in Civil 3D, so that then we can be able to enrich our understanding all together. After that, we have a sag curve. You will notice there is transition. So we will always connect the sag curve and another crest curve with a straight gradient. And then, of course, the sag curve is a little bit of a concave, whereas the crest is a convex. So you can see the parameters that the geometry is the same, but then one is moving in a clockwise direction, while the sag curve is moving in an anti-clockwise direction. Please take note of that, because as we go into the design now, we'll be needing those parameters right away. Now, once that is done, we understand that. I want us to look at the first thing, which is the key aspects of vertical curve. Number one is the minimum length of the vertical curve. These are the key aspect or key design parameters. The first one is the minimum length of the vertical curve. So as the design engineer, you must be able to know what is the minimum length of the curve that you choose or that you're using in your section. The second thing is the required sight distance. And in this case, we talked about stopping sight distance, passing sight distance, and headlight sight distance. We will be also talking about the driver's height. Of course, we always consider a height of 1.08 meters. And of course, the height of the object that we expect possibly to appear on the road. Now, let's talk about crest curves in particular. There are two conditions when we are considering the minimum sight distance criteria for vertical crest curve. The first condition, and I want you to take note of this, these are two conditions. And as you do your design, you must be aware of which scenario is applying where. So the first condition is where the sight distance, let me underline that so that we can stay guided. Look at this one, where the sight distance is less than the length of the curve. I don't know whether you can picture that. The sight distance that is required for that section is less than the length of the curve. So what that means, let me go back here, possibly. So let's say this is the crest curve. And this is the length of the curve. And let's say we want to use LS, or rather S, as the length of the sight distance required. Let's say stopping sight distance. The scenario says the length of the curve or the length of the sight distance is less than the length of the curve. It means the stopping sight distance is within the curve. This is the first scenario. The second scenario is where the sight distance extends beyond the vertical curve. The sight distance extends beyond the vertical curve. Now, let us give it, let's put it in numbers here. So it means the length of the sight distance is somehow beyond the length of the curve. So that means, and I mean, if you picture that, I want to stop and hear what would be the ideal scenario when it comes to design? And what is the implication of each of the two conditions from your perspective? Please, let's share. The session is open. Let's get to hear. What do you think? What happens? What happens?
Hello?
Yes, Jefferson? Hello, Jefferson?
I would say for design, it's better to consider the second scenario. Hello? Can you hear me?
Yes, I can hear you.
Yeah, I was saying for design, I would think the second scenario would be better because. Okay.
Why?
I'd say the
Why?
second
You need to
scenario
support your
where
answer.
you can see beyond the curve.
Okay,
You
that's
have
very good.
better sight because you see, if you in the first scenario, you may not have clear sight of as you pass your PVS, you're going towards now the PVT. You might not see clearly whether a car is oncoming or not. But when you can clearly see beyond, you'll be able to gauge whether or not there's any obstruction or maybe a car coming towards you.
Okay, thank you. Someone else? What is your reasoning around that?
Hello, everyone.
Hello.
Yeah, actually, also I agree with the previous discussant. Like, for example, for the crest, you that if the length of the set distance is less,
You are not audible, please.
But then
you may.
If it's more than the length of the curve, you realize. Yes, please.
You raise
Hello?
your voice. We are unable to hear you. You are not clear.
Can you hear me?
Yes.
Can you hear me?
Yes,
Okay,
yes. You are now closer to your mic.
Yes, I was saying that I agree with the previous discussant in that when the length of the set distance is greater than the length of the curve, you realize, like now for the crest, you won't be able to view clearly what is ahead of you because the crest is actually blocking you. But when the length of the set distance is less than the length of the vertical curve, there you're safe. You can be able to see and you're able to stop very well. So I agree, for better design, LS is supposed to be less than the length of the curve for it to be safe as you're moving around the road.
Jovin, I think you are contradicting yourself. Your conclusion does not go hand in hand with your argument. Anyway, thank you. One last person with another opinion.
My own opinion, please. I'm Osinachi. My own opinion. If you have that involves vehicles coming from both ways, you know, when the vertical curve is less, it might cause hold-on collision. There might be a collision. But when it is it is extended, when it is very far, you find out that there will be the side distance will be very, very clear. Nobody, they won't be able, because the curve will be cut to the minimum level, so that giving a side distance whereby the vehicle coming in the opposite direction we see each other without head-on collision. But when it is less than the vertical curve, it therefore means that they must really be, especially at the crest. Especially at the crest. So I go with the second option.
Thank you very much. I think that is that's a good argument. So I will proceed as we go. We will be getting answers to that very one. So please, if you also have another opinion, please make sure that you share it in our in the chat box, so that then we can be able to discuss them all together. So now I want us to look at the road design manual, because I don't want us again to, I like counter checking. This is a sample design for the vertical curve. Oh, let me share my entire screen. I noticed that we are unable to see. This is a design for a vertical curve, another vertical alignment design. And as you can notice, this is the first section. This is what we are calling a straight gradient. And then after that, we have a crest curve here. So we will notice the length of the curve is indicated. And then we have another straight gradient. And after that, we have a sag curve. And then after sag curve, you have another vertical curve. We have a gradient, a sag curve, another gradient, then a vertical curve. And then that continues all the way to where we have at the last gradient of the section.
We can't see anything in the screen. Oh, okay, I can.
Can you see my screen?
No.
Yes, yes.
Yeah, it's true, engineer.
Yes,
we
I think
can.
we're just
Engineer,
having a
we can
problem
see
with
you.
the network.
Okay, thank you very much. Thank you. Yeah, very well. So I was demonstrating now what we are talking about. This is the straight section. We said that the gradient is indicated in percentages. And then we have, okay, you can also decide to indicate it in ratio, 1 is to something, but then that becomes a little bit difficult for many people to interpret. Then there is the crest curve that we have here, and it has some parameters. We'll get into the details of them right now. And then there is the sag curve, and the green section is a bit of a fill. And then the red section that we are having here is a bit of a cut. It's a cut section. And you can see our maximum slope here is at 4.90%. This other slope is at positive 2.26%. I think that the 4.06 is the highest gradient that we have. Now, before we proceed, I want us to look at some guides that we have, because as you do your design, one of the key major things, while you have opinion and argument, it is also important for you to counter check with the various road design manuals and codes that we have in various scenarios. So this is the design of crest curves. Two conditions exist when considering. This is the Kenya Road Design Manual. I'm going to be sharing a copy with you. I think I shared sometimes on LinkedIn, but I can share with you at any time. These are public resources. Two conditions exist when considering the minimum sight distance criterion vertical curve. The first is where the sight distance S is less than the length of the vertical. And the second is where the sight distance extends beyond the vertical curve. Consideration of the properties of the parabola results in the following relationship. So this is just an equation that calculates. But you will be able to notice they are saying for sight distance where it is less than the length of the curve, this is the most common situation in practice. I hope you can note that. Let me highlight it. We will understand why we are saying this. And then I think this one gives now a table that is giving a bit of a summary of the minimum values that we use in design. But I will get to this at just now, don't worry. But I wanted you to understand that the manual has highlighted that the scenario where the site distance is less than the length of the curve is the most common situation when it comes to practice. The other situation is a bit rare when comes to the actual practice. But we'll see. We will do some calculations today so that then we can be able to justify why did they make this comment, this point. All right. So I'll go back to this part so that we can proceed and understand how we select various parameters. Now, you remember we said that when we are the vertical curves are defined by the parabolic equation. And the parabolic equation, what it does, it allows for gradual change in the curvature. So, and when we are talking about the change in curvature, basically, let me try to see how we're breaking it down. Now, remember, when we are moving along a section, we have the horizontal distance, and as we are moving horizontally, we are also having a change in elevation at that point. So that means then we have a scenario. Let me say, this is the kind of movement that we are having. Remember, this is the horizontal distance. These are the changes. This is kilometer 10, kilometer 2, but you are moving along this rate. So for example, if you wanted to know the rate of change, then it means you need to get a gradient at this point. So there will be a change in horizontal length, and then there will be a change in elevations altogether. So then it means if you wanted to get the rate of change of this section, it will be HL over, or sorry, the change in length or a change in horizontal, or rather in horizontal distance, change in horizontal length, the ratio between change in length to change in elevation at that point. And then that is what gives us a factor called the K value, this relationship. Let me show you, we will jump quickly to the American standards. I think the Kenyan standard does not give a bit of an explanation on that parameter. That rate of change, hey, please, can we mute? The rate of vertical curvature is the length of the curve per percentage algebraic difference in intersecting grade. So that is why we are saying if you get the percent, you try to get the gradient of that curve or any point along the curve. Let's say again, this is the curve. You want to get the gradient at any given point. It will be the change in length, horizontal distance, of a change in difference in elevation that I'm using. Then this gradient is what we call a K value. This K value is what we use in design of roads to ensure that we take care of the rate of change of curvature along the section. Now, these K values is what is imputed in the software. And I want us to have a scenario where we are saying, let's say our design speed is 80 kilometers per hour. Our design speed is 80 kilometers per hour. That is always the main guiding principle when it comes to choosing the design criteria for your road. Now, this is a table from the Ashton Green Book. and we have a design speed of 80 kilometers per hour. Let's say we are choosing a design speed of 80 kilometers per hour. Now, the stopping sight distance that you need, and remember we said it is the major controlling factor in the design of crest curve, is 130 meters. That is the stopping sight distance. Now, what this means is if a driver is driving on any crest curve that we design, and they see an obstacle anywhere ahead, they will require 130 meters to bring the vehicle to a safe stop without colliding with that object. They will require 130 meters. Let me know whether something is an issue. Okay, very good. Thank you very much. Thank you very much. I think everything is clear. So we have known that the stopping sight distance for a speed of 80 kilometers is 130. There is a formula that, of course, is used to calculate. I don't want us to go into the calculations at the moment. I don't want us to go into calculations at the moment, but at least we have the stopping sight distance. Now, I want you also to note this K value, which is the rate of change. So then it means the rate of change of vertical curvature within that curve at a speed of 80 kilometers per hour is 20c. Please note that down as well. This is what is called developing a design criteria for your vertical curve. So that then, as you go into your design, you have parameters that you'll be inputting in Civil 3D. Now, I remember Ossi asked a question and said he was wondering, how do I design a proper crest curve for my section? These are the considerations. First, you must get the first principles right. The road design manuals gives you the first principles. These are irreducible minimum to ensure safety, and mostly safety of the road user. So at a design speed of 80, the stopping sight distance is 130, and the K value to ensure a consistent change in the curvature of the curve is 26. Note that down. Now, let's go back and look at the Kenyan Road Design Manual. I want us to look at the Kenyan Road Design Manual here. And you can notice that we are comparing the two. You are comparing the two. At a design speed of 80, the K value for stopping sight distance at this point, they have provided 45. Now, remember, there is what we call the passing sight distance. And I remember one of you said that this one ensures we take care of maneuver. That is, when the person wants to overtake, of course, there is overtaking sight distance at that point. And then also for vehicles that are moving in the opposite direction. So can they be able to pass? Can they be able to overtake the next vehicle? Now, what you will notice is our factor, according to the American standards, was 26. When it comes to the Kenyan Road Design Manual, is 45. Now, the local manual in that country supersedes the international. So that is why, if you are in Kenya, then your design value, K value, will be 45 and not 26 that we have in the American standard for a design speed of 80. If there was no local manual in Kenya, that is when we will have considered the hashtag. Traditionally, in the old manuals, we are creating a context for your respective countries. So please don't localize this to Kenya. Even in your country, if you don't have a parameter or a specific consideration or a regulation about a specific design element, you have the right as a practicing professional then to reference a superior manual. In this case, the American standard is a bit superior to the local. But if there is a local standard, then the local standard takes precedence and not superiority. It takes precedence because then it has been developed with a keen consideration of the local conditions. Thank you very much. Now, please note down those parameters because we're going to be using them. I want now to quickly go to the crest curve.
Okay, to ask a quick question now.
Yes.
Why do you say the American manual is superior? Just wondering.
It has a more global adoption. It's about adoption. It's not about
So,
superiority in military power.
true, but what I meant is is it the fact that more people use it, does that mean that it's superior? I was thinking in terms of how is it superior in terms of the engineering, not so much the numbers that use it.
Sorry?
Like in terms of the engineering, what makes it more superior? Is it just because more people use it? Is that why you said it's more superior? Or is there any special engineering aspects considered for you to say it is more superior?
Definitely, it's when you talk about it, the first one is adoption, and the second one is also the level of detail that we have in the manual. It has a lot of a statistical approach to deriving the various parameters. You can look at it, and then the last one, okay, in terms of research, the last one is of course about update. They update their manuals more frequently, and they are also taking care of the current conditions. So we'll jump to the design of sag curve. Now, when it comes to sag curve, remember the crest curve, they mostly take care of the safety aspect and the blind spot. And then the second one is the sag curve. When we are talking about sag curve, we need to think of it in terms of one, drainage is the major aspect. Because you will always notice that it is more often that you find the drainage structures are located along sag curves. Why? That is where you naturally find waterways and you find provision for outfall. That is where you find bridges. That's where you find culverts. That's where you find many outlets to various catchments. While, of course, the crest curve also have a consideration on the drainage. Mostly, you will notice that when you provide a drainage structure at a crest curve, it is sometimes more of a river that is splitting some water so that it can go downhill and also across the road or section. That's just an observation according to the topography of most of the areas. But then, of course, you will find there are exceptions. But over and above that, there is an aspect that is called end light. So where the only source of illumination is end light and end lamps of the vehicle, the illuminated areas depend on the height of the end light above the road and divergent angle of the end light beam relative to the grade of the road. So what this means is when we are designing sag curve, we look in the aspect of illumination. So you ask yourself, will my road be having street lighting? So you'll notice many roads do not have street lighting, especially in the African context. So then you will be talking about how will the vehicles be operating at night. That is the aspect of road safety. So you will find that if the curves are not well designed, road users always complain of headlight glare. They also complain about discomfort. So let me paint a picture. We'll use my screen here to just make a sketch so that you can see this. So let's say we are having a downgrade, and then we're having such a scenario. So these are long gradients. So this is a long grade, and this is a long gradient. And you are having a short sag curve. It will be very uncomfortable for road users to drive through such section. So comfort is a major aspect when it comes to the design of sag curves. Now, the second aspect is again now the end light distance. So you will notice if these ones are a little bit steep. Okay, this is of course an exaggeration so that then it can paint a picture. When a vehicle is at this point, let's say a vehicle is located at this point. So this will be the line of, let's say that's the line of the end line. So then if another vehicle is at this area, please you may mute. We Kennedy, Modibo, and everyone, please you may mute. It will serve us. So if a vehicle is driving downhill at this point, you'll notice that they will be having headlight glare at this area. And the same scenario happens. But then if the road is a little bit, the curves are a little bit gentle as possible, you will notice that the angle here will be uneven. And therefore you won't be having much of headlight glare at the crest curve. Kennedy, please, you may mute. Unless you have a question, we can give you the mic, please. Guys, it is good also to have uh, we have dedicated time here to share knowledge, and you just come here to unmute. It's not right. Lahati, please. Lahati, you are distracting us. Would you just mute?
The admin can just mute them if they are not muting themselves.
Probably they logged in and they forgot. You can just mute them, the admin.
Engineer, you can make me the co-host and I'll tackle the rest.
Thank you. So we will finish it at that on crest curve. So we said that the major design aspect is of course the driver comfort and the end light. So we'll notice now the K values that we have. Let's say we are using again our design speed of 80. You'll notice the K values for driver comfort are 16 and for end light are 32. So then when we are designing, especially for sections that we are not going to have, traffic lighting or illumination on our section, then we use the K values for the headlight distance, that is a K value of 32 for a design speed of 80. Remember then, this principle can be applied for various, for other aspects of your, for other design speeds that you possibly might be having along your section. So thank you very much. I want now to finalize it with a few rules of the thumb that I have been able to. Okay, now before that, we have the other aspect, which is the length of the curve, the length of the vertical curve. It is called LVC. So remember, we have ended the design speed. It has given us the stopping sight distance. It has given us the K values for crest curve, sag curve. And now at this point, I want us to talk about the length of the curve, which is now the last parameter, especially when it comes to the design of these curves. So when we talk about this, the aspect is in difficult situations, and I want you to listen to this statement. In difficult situations, vertical curves approaching the minimum may be considered where the cost of providing large curves make their use prohibitive. Now, what this statement means is when you're designing form or you're designing crest curves and sag curves, we mostly make sure that we are not using the minimum parameters. We are a little bit above the minimum parameters. So even as, and you will notice it actually, it's a practical rule of the thumb. As you do your design, you will notice that the crest curve, the K values are way above 45. You will notice they are sometimes even around 180, 90 or thereabout. At the same time, you will notice that the stopping sight distance, of course, will always be less than the length of the curve. Now, this is the rule of the thumb. If you look at this table, I've extracted it. I think I'm offline. Okay, okay. Please be on the lookout so that I don't go offline. I don't know whether my internet is unstable. The minimum length of the curve, for example, for a design speed of 40, you can see is 80, 60, 100, 80, 140, 100, 180, 120, 220. The rule of the thumb for the minimum length of vertical curves is always 2 times the design speed. That is the rule of the thumb. And I want you to see it. For a minimum design speed of 40, we are seeing it as 80. For 60, it's 100. For 80, it's 140. For 130, it's 240. So if you follow that rule of the thumb, you will always find yourself adhering to 2 principles. Number 1, your curve will always be of above the minimum length provided as per the first design principles. Number 2, your curve will always be above the stopping sight distance. Stopping sight distance. Now, I want now to make a case for the people who argued that, or people of the opinion that the stopping sight distance should be outside or extend beyond the curve. Now, think of it as this scenario. Come back to that red vehicle of yours. We said it's a red Lamborghini driving up a crest curve. And at that point, your design stopping sight distance extends beyond the length of the curve. Now, this means the length of the stopping sight distance is greater than the length of the curve. Let's say we are designing a curve at 180 kilometers per hour. The minimum length of that curve we are operating on minimum conditions for now, just to create the case for you to visualize. The stopping sight distance is, the design speed is 80. The minimum length is 2 VD. So 2 times 80, that becomes what? I don't know. What is the length of that? Is 360 or what is that? Is
2
that
times
one?
8 is 160. 2 times 8 is
160
160.
meters. 160 meters, okay? That is now the length of the curve. Now, if you look at this snip of the American standards, you will notice that the stopping sight distance is 130 meters for a similar case. So our stopping sight distance is 130, and the minimum length is 160. So if you end the sight distance greater than 160, in that red label, it means if you see an obstacle within that curve, you will need a distance greater than the length of the curve for you to see. Therefore, it means the driver cannot safely bring that vehicle to a stop within the curve. That takes us to this very picture that we are having here. Now, the designer has provided insufficient, the driver has provided insufficient distance to stop. It means the stopping sight distance extends beyond the length of the curve. The result, you will be able to kill these cows. Jefferson, Jonathan, I think it's Jovin, sorry. Am I making sense to you? Do you now see why it was written as the common practice is where the sight distance is within the length of the curve? As the
I am
common
not
practice.
Jovin. I am not Jovin, but it makes a lot of sense. You want to be able to stop within the curve. It is safer that way.
Thank you. OC, can you now see things making sense to you?
Yes.
Thank you very much. Thank you very much. So then, the most ideal scenario is when the sight distance is within the curve. So you can see, whenever you see any obstacle within your curve, you can be able to safely stop. Now, if the sight distance is beyond, exactly what is in this picture is what is going to happen. The driver is not going to have enough distance to stop, and therefore will end up causing an accident at that very point. Now, that brings us to the climax of this section, and therefore we have been able to talk about the major aspect of the sag and crest. So I want us to briefly look about the gradient section. So the gradient is majorly where we have the rise or fall on any length of the road. And of course, it is going to influence the design speed. And of course, the terrain is the major factor. So sometimes you have very little you can do other than now move earth, invest in massive earthworks for you to achieve some of the gradients that you need according to the various classes of roads. Also, this gradient takes care of water or rather drainage on your section. So for example, we say to avoid standing waters on side ditches, you need to have a minimum gradient of at least 0.5%. So I will just give you a picture of these suggested maximum gradient for various paved sections. When we are designing the gradient section, and I want you to remember it is the straight section, we have the consideration of number one, the kind of terrain that we are in. So because it is, you cannot impose a certain design gradient without considering the terrain. So the kind of terrains that we have is number one, we have a flat terrain. We have a rolling terrain. So flat terrain is the one that has a slope of between 3 to 5%. It's actually, 3 to 6%. And again, when we are designing for gradient, we consider the classes of roads that we have. So as I earlier said, I remember I told you that when we are designing for higher classes of road, the government opts to invest much more into the cost of construction so that then it can be able to reduce the economy of transport for the road users in the long term of that section. So that is why you will notice that these gradients are limited to specific. So we're having absolute. So for example, Joy, I think you're writing on my screen. Thank you. Now you know how to use the pen. So we have a flat terrain for design class or for a class of road A and S. This majorly means heavily trafficked roads. We are having desirable of 3% and an absolute of 5%. So if you go to a lower class of road, these A, S, and A, they are called international trunk road. Then when you go to B, which are mostly national roads or regional roads, then that one you can be able to use a desirable 4 to 6%. You have various terrain. This is a rolling terrain. A rolling terrain is a terrain that is not flat. It has a mixture of flat to a bit of an hilly section. And then there is the mountainous. So the mountainous terrain is where we have a bit of mountains. We are limiting this to an absolute of 9% for high international trunk road and a maximum of 10% for regional roads or national roads. Then you will be having, of course, escapement. Escapement is majorly where we have very, very steep sections. And you can see we are going to a gradient of up to 10%. When you have not been to site, you can be able to say like this 10% is very small, but a slope of 10% is quite steep, to be honest. And then again, remember, when you're designing for this vertical alignment, and especially on this section for gradient, you always have a consideration on the largest, which are the major vehicles or vehicle characteristics, the characteristics of the vehicles that are using your section. So if you find yourself with a lot of heavy-gun vehicles, articulated trucks, then it means you don't have an option other than using as minimum gradient as possible for the section. Then we have urban section. So we include urban as its own kind of a terrain because it has unique requirements. You know, it's very interesting for you. You know, I don't know, there is a hill on a city or something. But then when we are in urban areas are more pleasant. And when they are a little bit, you know, having some desirable slope for that section. And of course, these are the recommended section. But there is an important option, a note there, where there is freeways, expressways. We always have the maximum gradient should not exceed 4%. Expressways and freeways, the maximum gradient should not exceed 4%. I want you to look at all the expressways in your countries. You will always notice that the gradient is quite few for that matter. So for our section today, we are going to assume you are working on a rolling terrain. Atakunda, thank you very much. Zach Mohammed, thank you. You may now stop using the whiteboard. So we'll be using a rolling terrain, and it means we are considering a class A of the road S. These are high traffic road, and then our terrain will be between 5 to 7% for that matter. So in this simple presentation, you've been able to develop what is called design criteria. Now, this design criteria is what guides you in the design of your vertical alignment. And we're going to be doing that in a few. Then after you list down, you have what we call a technical report, design report. So then that is where you argue, you put down your judgment, your considerations, and the constraints that you're going to have considered as you arrive to those various factors. Now, let's go jump straight to the software. This is an amazing terrain that we currently have here. I'm not going to spend a bit of time trying to do the obvious thing, like, for example, creating the profile. I want just to go into the design of the vertical profile, and then I will give you an overview of how the design is actually done. So what I'm going to do, I'm going to delete my vertical profile, the one that I've designed, so that then I can show you how we can design it together. I don't have a problem deleting that, so let me delete it. I think I was using it in the corridor modeling, but let me just delete it so that we can start together. Now, this is a road profile, and this profile is giving us the OGL. So this is a representation of my OGL. In a scenario where you're finding that your OGL is broken, it means that your alignment is somehow moving away from the section where you have your surface data. So then it may need a little bit to be looked at in that scenario. And I think that scenario is specifically somewhere here, where my alignment is moving away from the surface of the section. But that is something that can be corrected later on. So when you're designing your section, it is important to know that when you're designing your road profile, at this point, you will be designing what is called the formation level, not the finished road level. The formation level is basically where you have done to your final earthworks of your section. So at that point, you'll be able to get the finished, or rather the final earthworks. You'll be able to get your cut and fill at that very point. The other scenario is the guiding principle is always to design as close as possible to the existing ground, because then there is the principle of value engineering. You want to make sure that you are not just imagine a scenario where someone just came and decided, now I want to start okay, let me use a visible let me use a little bit more of a visible layer. Let me see the one that is in green. Very well. So in approach to design, you cannot just come and decide that you want you want your profile to move at that point. You cannot come and decide that you want your road profile to be moving at that point. No, your starting point is the existing ground. So first, make sure that you flash your design section, your design level with the existing ground. And then now, with the considerations that we'll be looking at, drainage, safety, stopping sight distances, you keep adjusting. And then after that, you can be able to incorporate the various fill layers that we have in the section. So let me go straight into how the approach or the workflow in Civil 3D. So after you have your profile, sorry, I was about to end the meeting. I was about to end the meeting by mistake. Apologies for that. I wanted to hide this so that it doesn't distract us. So we go to the home ribbon, and the home ribbon, create design panel. You will find there is profile, and then you're going to create profile. You will select create profile creation tools. Under profile creation tools, it will ask you to select the profile view. Remember, this graph is what is called a profile view. So you will have the create profile dialog box. So you'll see the name of the alignment has been selected here. This is the alignment that was used to create the profile. And there's the name here. We are going to call it formation level. And once we do that, there is, of course, the design, the profile style. Profile style, you can always choose a profile style that is existing. For you, it will be design or layout, but then you can always customize them to have your own. So I'm going to use the UNRWA design for now. And then the profile label set, you can use what we call the complete label set. For you, I think you have that in your software, and it is always it's a custom one. But before that, we always set the design criteria. So the design criteria allows us at least to be able to check against the AASHTO standards. Remember, this one is coded according to the American standards. And therefore, make sure that under design criteria, you can be able to activate it. Once you activate that, you can use the design criteria file you want to assign. And in this case, you can be able to use even the 2018 metric roadway design standards. Again, this is the American standards that has been integrated in the software. For those of you who have currently, for example, those who have country kits, like for example, you can see here, this is the UKIE. If you are in the UK or Ireland, you have you currently have a kit. You have integrated your road design manual into the into the software, so you can be able to select it. I think also South Africa, India, Abu Dhabi, or rather what we call the United Arab Emirates, and many other countries have their country kits. For those of us who don't have our country kits, you can use the American standard. So we will use the American standard for now and get to open. Once you do that, you will come down, of course, you will find the minimum K values. The K values are the major ones, are the major checks, and we're using the AASHTO 2018 standards. You can activate the design check set. I will be able to do another session about design check set. And for you, it will be the standard. But for me, I had already created a design check set that I normally use to run the checks here. And then press OK. Once I press OK, I will have the profile layout tools. The profile layout tools allows us now to design our road section according to our the design criteria that we developed along this presentation. I'll just briefly take you through the tools that we have here. The first tool that we have is what we call draw tangents. This is now what we use for the straight sections. I'll show you, for example, there is a section where we have draw tangents, and I will normally start at the very start point of my road section. You zoom it as much as possible to have it there. And then you will estimate where your straight road section ends. So for example, for mine, I see it at that point. So at that point, you will have given the formation level. Remember, you want it to be as level as possible with the existing ground. So I think that's the best outfit I can have. The first thing you'll notice is once you draw it, it will give you the gradient of your road section. So for example, this is a downgrade or a downhill gradient of negative 2.29%. You will notice at the start of the station, it will give you the grade brick station. This is where you're starting your section. At this point, this is kilometer 11 plus 00. And it is also going to give you the elevation at that specific point. At also the end of your straight section, you have the station and also the elevation at that specific point. What you remember, I want you to remember this, the layout that we had for vertical alignment. And let me just draw it with polylines here. You remember this is how it looked like. Let me change this to an arc. and then change this to, let me see, line. So if you remember very well, this was the geometry of our, this is the geometry of our curve. That is a vertical curve. This is a crest curve. If I want to have a sag curve, I can just be able to mirror this. Let me put it there. Very well. So this will be a sag curve, and this will be a crest curve. So a crest curve, we have the gradient. So this is what we are putting here. So it means for us to conclude it, we need to have another gradient at this point. So I'll just draw another gradient from this point to somewhere like here. And you remember, I'm also not making sure that it is going as closely as possible to the existing ground. So if I was designing this curve, I have already taken care of the first gradient and the second gradient. Now, remember, as we noted when we were developing the design criteria, for a rolling terrain, our maximum gradient was supposed to be 6%. So I'll come here and check this is within the range. And when I look at this other point, this one is coming to 6.0%. So I don't want to operate at that. So then I can level my ground a little bit on that side. So let me raise it a little bit at that point so that we see the final gradients that I will achieve. So what is left of me, again, remember you need also to, you can always extend these tangents if they are not fixed. So you can always extend them. It is your judgment where you see the curve. Remember, you're going to build on the ground. So this is how the ground looks like. So you make sure that as you position your tangent, you position them in a manner that it will give you allowance to draw your curve at this point. So this is a crest curve. For you to draw crest curve, you will find a section where there are curves. So you will find the icon for curve. And we said that vertical curves are defined by the parabolic equation. So at this point, we are going to use the free vertical curve parabola. We select that. The software is going to ask us select the entity, the first entity. So the first entity is always the tangent on the left that you started with. So this is it, the first entity. Then we select the second entity, which is the tangent on the right that we selected. The software will ask you to specify the curve length. So I want you to make sure, please note that as you do your design, the software is communicating with you through the command line that is at the bottom of your screen. So it is telling us to select the first entity. Let me just repeat to make sure that everything is right. So when you're starting to design your curves, you already have your existing ground. Then once you have your existing ground, you keep in mind, number one, the geometry of the curves. Sorry. I think my network disconnected a little bit there. I'm sorry about that. So I was saying, I was giving you the thought process of how you need to approach it. Please note this. So the first thing is we have already developed the design criteria. The second thing is to keep in mind the geometry of the curve. That's why I've drawn this thing here. So this is the tangent, a curve, this is the crest curve, and then a tangent on the other end. That is the geometry. Now, I need also to note down the gradient here. That is the minimum for this section and the minimum for this section. After that, you know that now I need to connect these two tangents with a curve. It is important to note the direction. So if you started from left to right, everything that you do will always start from left to right. If it is a little bit challenging for you to start designing your road from right to left. I don't know why. I think people naturally move from left to right. Anyway, this is my personal opinion, but I'm starting from left to right. So even these tangents, as you draw them, please remember that you must draw them from left to right. If you start from right to left, you can, when you come to connect that tangent, it will not be possible for you to connect the two tangents. Please note that with a curve, because now the curves are the tangents are moving in opposite direction, and therefore cannot complete the geometry at that point. Now, at this point, we want to connect now the curve itself. When connecting the curve, we go back to our design criteria and look at the parameters that we used. So the parameters that we developed were, number one, the length of the curve. The minimum length of the curve, we said it is 2 VD. 2 VD means twice the design speed. So the length for this section, I remember someone telling me for a design speed of 80, it will be 160. That is the minimum. Now, we note that down. We also note down the K value for a crest curve was 45. We note that down. Then after we note down those parameters, we'll come to the profile layout tools and we go to the curves. We will select free vertical curve. Please select that. And it will ask you, please take note of the command line. So we have select first entity. So the first entity is the first tangent here. You select it. Please make sure you zoom and select it. Then it is telling me to select the second entity. I'll zoom in and select it here. Now, at this point, we want now to connect with the curve. The software is telling me specify curve length or radius or pass through or plane. We are going to design using all of the methods. So I want us to start with the curve length. So with the curve length, we know that the minimum, I think that is the active command. The minimum now is 80 times 2, which is 120. So 160. So I'll input 160 meters, press enter again, and my curve will be completed with the minimum requirements. That is it. So we already have the curve with the minimum requirement. Now, what you do before even you proceed to do the other curves, it is always important for you to counter check again with your design criteria. So my design criteria said this gradient here is good. The curve here looks cool. So you can see the length of the minimum length of the vertical curve is 160, and the K value is 43. You will notice that when we were in the road design manual, the K value was supposed to be 45. So we need to modify that a little bit. But then you will notice again, the gradient at this point is somewhere about 5%, which is also within the limits that we said for a rolling terrain. Now, when you do this, you design this curve, you have the option of adjusting how it looks like. For example, one of the rules of the dump is do not fill at a crest curve. What this means is, this is already a mountainous section. Why are you filling? Why are you handing more material in another mountain? I mean, it's common sense. The second rule of the dump is do not cut in a sag curve. Again, it is already down. Why are you digging even deeper down the pit? So these are just but rules of the dump that are obvious. Of course, there are exceptionals depending on the geotechnical and of course various other parameters that you may need to take care of at that point. Now, that is it. Remember also the manual said we only use the minimum parameters in scenarios where it is difficult to achieve larger curves. One of the things you will notice with this curve, it looks a bit steep and it is above the OGR. So we need to lower it a little bit and possibly make it gentle. This is again about judgment. So for example, I can use this knot to lower it a little bit so that I can achieve a cut because this is an in section. and you'll notice the curve has moved to this point and the K value has increased. So the K value again is dependent on the steepness or the gentleness of the curve. So if you want your curve to be a bit gentle within the section to morph with the existing ground, then you increase the K value. If you want it to be a little bit steeper, then you reduce the K value. How do you do that after you do the design? In the profile layout tools, you will notice that there is something that is called the profile grid view. Select that, and you will notice that you can be able to access the parameters of your curve. So for example, this is the first tangent. So we have the number, the PVI, the elevation, grade in, grade out, change in gradient, the profile curve type and all of these parameters. So you can see the first one, the gradient is -2. The second one is a curve. Anytime you select it here, you will find a green triangle. This green triangle is always positioned at the center. This is called a PVI. It is positioned at the center or the point of vertical intersection of the two gradients, or rather of the two tangents of that curve. So you will notice this is the curve length. You can increase the curve length. Let's say you want the curve length to be 200. And you notice now this curve becomes a little bit longer. You want it to be longer. So a longer curve is a little bit more aesthetic, and it will also provide the comfort of the road users. Again, you can modify the K value. You will notice, for example, if you wanted to have a K value of, let's say, 65, you will achieve it. Now, what determines the number of K value is, for example, you can see how this is perfectly morphing with my existing ground. The curve lies so perfectly with the existing ground with a minimal cut, and this looks like also kind of a burden material that I'm going to remove on this section, and then I will have one of the perfect curves that I have. So there are necessarily no maximum K values that you need. There is no maximum curve length, for example, that you need. But then the ground itself will guide you on the kind of the profile that you're going to have in a specific scenario. Okay. Now let's proceed and design a sag curve and end the session at that point, because I can see time is not on our side. If I want to close this, I'll just close it from this point. If you want to delete an element, there is an icon with an X. You delete an entity. So I can delete that there. Very well. So I want to do a tangent. This is a sag curve. Again, you estimate and you imagine what if you were drawing this curve with your hand. Where would you draw the straight section? So for example, for me, I would draw the straight section from this point to here. I'm also considering this other curve that I'm going to have on this other side, because it looks like I'm going to be having another curve at this point. So I need to be a little bit more considerate. Remember also the position of your tangent. Don't position your tangent so deep into the curve. The software will give you no solution. So please position it a little bit outside the curve so that it is easy now for the software also to connect it for you. We'll go back to the crest curve, to the free vertical curve. I will select the first entity, and then I will select the second entity at this point. And at this time, I'm not going to use the curve length. I'm going to use the K value. Remember, that is one of the design parameters that we used previously. So I'm going to select K value. And once I select K value, this time I want to show you something. So I'm going to use a K value of 10. Press enter. And you will notice this is the scenario that I was telling you. Like, it just looks wrong, even from your look of things and from also the knowledge that we have collected today in this session. this one looks wrong in every aspect. Number one, we are cutting in a sag curve. It's not ideal. You don't do that here. Number two, it is a short. You can see the length of the curve is 93. Very, very small. It will give an impression of a king. It will be very uncomfortable for road users. There will be end-light glare at this point, you know. The end-light from this side and from this side to be problem for people to pass at this point. The stopping sight distance will not be accommodated at this point. Now, that is why one of the rules of the thumb is beware of short sag curve after long straight gradient. And this is a very good demonstration of that. So this is another long gradient. This is another long gradient. So you don't want to have sag curve. So how do we modify this again? We will use the grade view, and you will notice the software already knows, you know, it already knows that the K value that you have used is wrong. So that is why the exclamation mark here, the minimum K for headlight sight distance violated. And you can see it says that it should be greater than or equal to 18. That is when you hover your cursor on top of this exclamation mark. You scroll down on the right, you can see the minimum K for headlight glare has been violated. The minimum K for stopping sight distance. You will notice the minimum K value for stopping sight distance has only been assigned on the crest curve. Note that this is the type of curve here is a crest. And in this case, we are having the minimum K value for stopping, K value for passing, and K value for headlight. Under headlight, it is empty. When it comes to sag curve, you will notice that that is where the software is giving us. So the things that we have discussing are already integrated in the software, and it is intelligent enough to know that the main controlling design parameter for sag curve is the headlight distance. So let us modify that quickly as we end the session. So I can be able to modify this. I remember ours was around 32, and that's it. So 32, and you will notice the error, or rather the warning symbol here has already disappeared. You will notice also the length of the curve has gone way above the minimum. So the minimum is 126. Again, the reason or the rationale that we only use the minimum conditions at very, very critical areas is justified one more time. But then again, we are violating one rule of the thumb. We are cutting already in a cut section. So how do you modify this? You use node edit. So you can use this node here to just move your curve a little bit on the upper side. You know, these are now, you know, manual edit. You can move this tangent to that direction. And then move this one to this direction and move your curve. You know, you can be able to move the curve so that it is positioned where exactly you want it. You know, that's it. Now, after that, you will notice it has affected the other curve at the back. And now that is the work of a designer. Parameters here. So once this is done, you will notice the curve. The curve length has reduced significantly. So you can again be able to modify it even to something like 300. And you notice it covers very well, very nicely around this section. So thank you. I think that is basically my presentation up to this point. There is the aspect of drainage again. The gradient takes care of the drainage. But should we also be able to position our culvert at this point? There is what we call you account for something that is called the overburden. So the rule of the thumb again, the overburden should be the 0.6. So let me give you a simple demonstration here. So let's say we are having a culvert at this point. This is a pipe culvert. And in this pipe culvert, let's say it is a 900 mm. So, of course, this culvert will be placed on the OGL. That is the assumption. But also, if you go to site and notice that you will need to do a little bit of excavation, then you can be able to get a little bit more of exact figures. But this is just for demonstration purposes. So what you'll notice is, at this point, this will be the level for your culvert. Now, where you position your FRL is very, very important. Why? You must be able to account for the 0.6 meters. Now, the 0.6 meters, you start counting it in this manner. The first thing, you must be able to account from the top of the barrel, you need to account the ounching. That is like 150 mm ounching that will cover the culvert at the top of the barrel. So you do the 150. Then on top of that, that is where now you account the 0.6 meters before you start laying your pavement, to ensure that now the vehicle does not. So let me do 0.6. So you will notice that is 0.6 at that point. So this is, of course, based on the scale that I've adopted. So you make sure you account for it, so that now as you position your culvert, you will have derived the invert levels from your profile. So for example, let's say, so we derive this point, you will go straight all the way to this other point on the profile, and you can be able to see the elevation for your culvert is at this specific point. So that is something we will cover more extensively in the course, how you position your drainage structures, how you put your culverts, of course, to ensure that then they are constructible and the invert levels goes hand in hand with the profile of your roadway. So thank you very much. I think that is the little that I had prepared for you to do. And up to this point, you've been able to take care of these parameters. Mostly the stopping site distance is very, very, very critical when you're designing your crest curves for any road section, and you make sure that you are able to achieve that. Thank you very much. That is it for me. And yes, the session is now open. Just before that, let me go to the chat box and see what I can say. Jovin says, I think the first scenario where LC is less than the LVC. Okay, I think that one we handled. Please do share the recording and the slides. Yes, of course, I'm going to be sharing it. Please share the recording. I'm going to share it in the morning, Jackson. The screen is not visible. I think now it should be. Okay, thank you very much. All right, thank you very much, Ajay. Thank you, thank you. Brian, the sessions are gold. Thank you very much. Sekani says, powerful session. Thank you very much, my brother. Wendy, I think, is a lady. Thank you. Bonnet, thank you. Very well. Okay. All right. Thank you very much. Iso, thank you. All right, James, thank you. I'm happy to know that it's worth your time. Diane Rose, thank you, thank you, thank you, thank you, everyone. Due to the interest of time, I understand that we are in very different time zones, and tomorrow obviously is our work day. I want to appreciate all of you. Thank you very much for your time and your audience. I hope that the session